Project Euler problem 12. Highly divisible triangular numbers. The sequence of triangle number is generated by adding natural numbers, and so the seventh triangular number is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, which is equal to 28. So the first 10 terms of triangular numbers are 1, 3, 6, 10, 15, 21, 28, 36, 45, 55. So if we list the divisors of those numbers until 28, we will find that the first one has only one divisor, the second one, 3, has 2 divisors. From 6 until 21, they have 4 divisors, and 28. For the first time, it has five numbers that divide that number. So here it asks us to find the first triangular number that has over 500 divisors. So here's what we actually do. 28 is in the sum of 1 until 7. So we know that triangular number, if you want to write them a recursive function, the recursive function would be like the f of n is equal to f of n minus 1 plus n. So it's just to make the calculation easier. There is one other obvious way that gives us each number directly. Like we can say that f of n is equal to n times n plus 1 over 2. Let me make sure if it's right. So for the first one, it will be 1 times 2. So f of 1 would be 1 times 2 over 2, which is 1. F of 2, with this direct equation, would be 2 times 3 over 2, which is 3. So there are 2 different ways. One straight way to find that sequence, and one recursive way. Why I use a recursive way? Because here I'm gonna use a while loop, and in while loop I prefer to, because I should create all the numbers. So it's much easier for me to use it recursively. It's not a recursive function. It's just creating them with the recursive method. So when we want, so one other thing that we have to take care of is to finding the number of divisors that each number in this sequence has. To find the divisors of a number n, we start from number 1 until the square root of that number. So we started from 1 until the square root of n. Because we want the number of divisors should be greater or equal to 500. We know that 500 is an even number, and the perfect squares has odd number of divisors. So we don't need to be worried about perfect squares. So then we start our for loop from 1 until the time that I times I is less than n. Well, as I mentioned, we don't care about square roots, so we don't need to put I and I be less or equal to n, because the equality here is not important, and ignoring that will not gives us a wrong answer, because we know that it cannot be. So it just cannot be a perfect square. I define the variable d to save the number of divisors. So each time I check for a number, I set the d as 0. And I define the variable count, which starts from 2, go to 3, 4, and it goes until the time we could find a number that has greater than 500 divisors. So our number starts from 1 for the first integer, first term of triangular numbers. The next term, it will be n plus equal to count. And I add count each time with 1, so count would be changed, and the n would be our triangular number. So, we start numbers with 1 because the triangle number starts with 1. And then these are number of divisors, and as the first one, the number 1 has only 1 divisors, so I put d as 1. And count starts from 2, as I mentioned previously, and the second number is 1 plus 2, which is 3, so count should be initially 2. So until d is less or equal to 500. So if it gets more than 500, then we are done. So each time I set d as 0, and in which is our next term of triangular number would be created by this method, n plus equal to count. And here's a for loop to check the number of divisors. So we know that each time it divides a number between 1 and a square root of n, there is another number that also divides n, that is n over that number. So here we have, so for each number I, that the modulo of n and I is equal to 0, there is another number n over I that also divides n. So each time I add d by 2, and each time the count will be increased by 1 to create the new term in our triangular sequence of numbers. So it will print out the answer at the end. If you run the program, the answer would be this: 76,576,500. And if you check the results, here's the same number. So that's the way to solve this question.